Evet, şimdi benim önümde açık olan Wikipedia sayfasında Mars Oxygen Through Experiments başlıklı İngilizce sayfa açıktır. Ben şimdi önce bunu Microsoft David'e bir okutmak istiyorum. Ondan sonra belki bazı yerlerini, mühim yerlerini Microsoft David'i susturup e, çevirme niyetindeyim. Şimdi öncelikle bir Microsoft David'in sesini alalım.
Mars Oxygen ISRU Experiment. 19 languages. Article. Talk. Read. Edit. View history. Tools. From Wikipedia, the free encyclopedia. Moxie redirects here. For other uses, see Moxie. Disambiguation. Mars Oxygen ISRU Experiment. Mars Oxygen In Situ Resource Utilization Experiment. Moxie. Operator. NASA. Manufacturer. NASA/Caltech/Jet Propulsion Laboratory Oxy and Energy. Instrument type. ISRU, In Situ Resource Utilization, Experimental Technology. Function. Oxygen production. Began operations. April 20th, 2021. Ceased operations. August 3rd, 2023. Website. mars.nasa.gov/mars2020/mission/instruments/moxie. Properties. Mass. 15 kilograms 33 pounds. Dimensions. 24 times 24 times 31 centimeters. Power consumption. 300 W. Host spacecraft. Spacecraft. Perseverance. Launch date. July 30th, 2020. Rocket. Atlas V541. Launch site. Cape Canaveral SLC-41. The Mars Oxygen In Situ Resource Utilization Experiment, MOXIE, 1 was a technology demonstration on the NASA Mars 2020 rover Perseverance investigating the production of oxygen on Mars 2 on April 20th, 2021. MOXIE produced oxygen from carbon dioxide in the Martian atmosphere by using solid oxide electrolysis. This was the first experimental extraction of a natural resource from another planet for human use. 1.3 The technology may be scaled up for use in a human mission to the planet to provide breathable oxygen, oxidizer, and propellant. Water may also be produced by combining the produced oxygen with hydrogen. 4. The experiment was a collaboration between the Massachusetts Institute of Technology, the Haystack Observatory, the NASA/Caltech Jet Propulsion Laboratory, with Oxy and Energy. Objective. Edit. MOXIE's objective was to produce oxygen of at least 98% purity at a rate of 6 to 10 grams per hour, 0.21 to 0.35 Os/H, and to do this at least 10 times, so the device can be tested in a range of times of the day, including at night, and in most environmental conditions, including during a dust storm. 1. Development. Edit. Overview. Testing. Installed. MOXIE builds upon an earlier experiment, the Mars In Situ Propellant Production Precursor, MIP, which was designed and built to fly on the Mars Surveyor 2001 lander mission 5. MIP was intended to demonstrate in situ propellant production, ISPP, on a laboratory scale using electrolysis of carbon dioxide to produce oxygen. 6. The MIP flight demonstration was postponed when the Mars Surveyor 2001 lander mission was cancelled after the Mars Polar Lander mission failed. 7-8. The principal investigator, PI, of MOXIE was Michael Hecht from the Haystack Observatory at Massachusetts Institute of Technology, MIT. 9. The deputy PI was former NASA astronaut Jeffrey Hoffman from the Department of Aeronautics and Astronautics at MIT. The project manager was Jeff Melstrom from the NASA/Caltech Jet Propulsion Laboratory, JPL. Along with MIT and JPL, major contributors are Oxy and Energy, previously Ceramatech Incorporated, and Air Squared. Other contributors include Imperial College London, Space Exploration Instruments LLC, Destiny Space Systems LLC, the Niels Bohr Institute at the University of Copenhagen, Arizona State University, and the Technical University of Denmark. 10-11. Principle. Edit. MOXIE acquires, compresses, and heats Martian atmospheric gases using a HEPA filter, scroll compressor, and heaters alongside insulation. 1. Then splits the carbon dioxide, CO2, molecules into oxygen, O, and carbon monoxide, CO, using solid oxide electrolysis, where the O atoms combine to form gaseous oxygen, O2. 12. The conversion process requires a temperature of approximately 800 degrees Celsius, 1470 degrees Fahrenheit. Forest Lead oxide electrolysis cell works on the principle that, at elevated temperatures, 12 certain ceramic oxides, such as yttria-stabilized zirconia, YSZ, and doped ceria, become oxide ion, O2, conductors. A thin non-porous disk of YSZ, solid electrolyte, is sandwiched between two porous electrodes. CO2 diffuses through the porous electrode, cathode, and reaches the vicinity of the electrode-electrolyte boundary. Through a combination of thermal dissociation and electrocatalysis, an oxygen atom is liberated from the CO2 molecule and picks up 2 electrons from the cathode to become an oxide ion, O2. Via oxygen ion vacancies in the crystal lattice of the electrolyte, the oxygen ion is transported to the electrolyte anode interface due to the applied DC potential. At this interface, the oxygen ion transfers its charge to the anode, combines with another oxygen atom to form oxygen, O2, and diffuses out of the anode 1. The net reaction was thus 2CO2, 2CO and O2. Inert gases such as nitrogen gas, N2, and argon, Ar, are not separated from the feed, but return to the atmosphere with the carbon monoxide, CO, and unused CO2-1. Mars experiment. Edit. MOXIE first Martian oxygen production test on April 20th, 2021. Graph. Oxygen production was first achieved on April 20th, 2021, in Jezero crater, producing 5.37 grams, 0.189 ounces, of oxygen, equivalent to what an astronaut on Mars would need to breathe. For roughly 10 minutes 13 MOXIE was designed to safely generate up to 10 G/H, 0.35 of oxygen 14.4 with theoretical production limited to 12 grams per hour, 0.42 of oxygen due to the limited capacity of the 4 ampere flight power supply. The oxygen produced was analyzed and then released back into the atmosphere. 15. MOXIE was used to isolate oxygen a further 9 more times over the course of approximately 2 Earth years, or 1 Martian year, in 3 stages. The first stage will further investigate the oxygen production, the second to test the instrument in a variety of times of day, seasons, and atmospheric conditions, and the third to produce oxygen at different temperatures, and alter the mode of operation to investigate differences in production. 4. On April 21st, 2021, Jim Reuter, the Associate Administrator for STMD, explained that the experiment was functioning with results having many uses, stating, "This is a critical first step at converting carbon dioxide to oxygen on Mars. MOXIE has more work to do, but the results from this technology demonstration are full of promise as we move toward our goal of one day seeing humans on Mars. Oxygen isn't just the stuff we breathe. Rocket propellant depends on oxygen, and future explorers will depend on producing propellant on Mars to make the trip home." 13. MOXIE had generated a total of 122 G, 4.3 ounces, of oxygen, about what a small dog breathes in 10 hours. At its most efficient, MOXIE was able to produce 12 grams per hour, 0.42 of oxygen, twice as much as NASA's original goals for the instrument, at 98% purity or better. On its 16th and final run, on August 7, 2023, the instrument made 9.8 G, 0.35 ounces, of oxygen. MOXIE successfully completed all of its technical requirements and was operated at a variety of conditions throughout a full Mars year, allowing the instrument's developers to learn a great deal about the technology. 16. Implications. Edit. NASA states that if MOXIE worked efficiently, they could land an approximately 200 times larger, MOXIE-based instrument on the planet, along with a power plant capable of generating 25 to 30 kilowatts, 34 to 40 HP, 1 over the course of approximately 1 Earth year. This system would produce oxygen at a rate of at least 2 kilograms per hour, 4.4 lb/h, 1 in support of a human mission sometime in the 2030s. 1718 The stored oxygen could be used for life support, but the primary need is for an oxidizer for a Mars ascent vehicle. 1920 It was projected, for example, in a mission of 4 astronauts on Martian surface for a year, only only about 1 metric ton of oxygen would be used for life support for the entire year, compared to about 25 metric tons of oxygen for propulsion off the surface of Mars for the return mission 13. The CO, a byproduct of the reaction, may be collected and used as a low-grade fuel 21 or reacted with water to form methane, CH4, for use as a primary fuel 22-23. As an alternative use, an oxygen generation system could fill a small oxygen tank as fuel oxidizer to support a sample return mission 24. The oxygen could also be combined with hydrogen to form water for technical specifications. Edit. Data from NASA, Mars 2020 mission Perseverance rover, Comma 9 Ceramatech and Oxy and Energy 25 NASA Jet Propulsion Laboratory 26. Main job, to produce oxygen from the Martian carbon dioxide atmosphere. Location, inside the rover, front, right side. Mass, 17.1 kilograms. Weight, 37.7 lbf, 168 N. On Earth, 14.14 lbf, 62.9 N. On Mars. Power, 300 watts. Volume, 9.4 in times 9.4 in times 12.2 in, 24 centimeters times 24 centimeters times 31 centimeters. Oxygen production rate, up to 10 grams, 0.022 pounds, per hour. Operation time, approximately 1 hour of oxygen, O2, production per experiment, which will be scheduled intermittently over the duration of the mission 9. MOXIE, Operational Design Drive, SOXE. Gas flow, internally manifold for O2 purity and DP. Feed, dry CO2 in a range of 30 to 80 G/HR. Product, 99.6% pure O2, internal manifolding. Structural, robust to survive launch, EDL shock and vibe, compression load requirements. Power, highly constrained. Mass, 1 kilogram max. Volume, rigidly constrained. Operation, 20 plus 120-minute cycles. Heating ramps, 90 minutes, C515 degrees C/hour, from ambient, potentially 40 degrees C, to 800 degrees Celsius. Heat application, heaters on end plates only 25. MOXIE, Materials Design Drivers. Interconnects, IC Powder Metallurgy, CFY, Plan C. Seals, glass seals. Current bus bars, brass rod/welded wire. Feed manifolds, inlet tube/internal manifold O2 purity. Anode electrode, perovskite. Cathode electrode, modified proprietary Cermet. Electrolyte, Scandia stabilized zirconia, SCSC, 25. MOXIE, cell design. Number of cells, 10, arranged in 2 stacks of 5 cells each. Oxygen production, 10 grams per hour, 1 G/HR per cell, 26. Each cell consists of electrolyte, yttrium-stabilized zirconia, YSC, cathode, anode, connecting cells, high chromium alloy, matched CTE to ceramic electrolyte, approximately 100 millimeters times 50 millimeters times 2 millimeters, 3.937 in times 1.969 in times 0.079. Manifolding for gas streams 26. MOXIE, gas delivery system, scroll compressor. Scroll pump compression rate, up to approximately 1 bar. Scroll pump RPM, low speed, 2000 to 4000 RPM. Performance, inlet gas, 83G/HR, P equals 7 torr, T equals 20 degrees Celsius, pin equals 120 W, mass. MOXIE, targets. Operational cycles. The primary mission requirements call for the capability to operate a total of 20 cycles 27. 10 cycles pre-flight. 10 plus cycles on Mars. Qualification and verification testing. It involves 60 full operational cycles for proof of extensibility, which is 3 times the number of cycles planned for the primary mission 27. Oxygen purity, 99.6% plus at end of life. Temperature capability, capable to operate at 65 degrees C proof temperature. Compression, shock, and vibe requirements. Withstand 8 knots compressive force. Withstand, PF, plus 3 dB levels for flight shock and vibe requirements 25. References. Edit. ABCDEFGHI Hecht, M. Hoffman, J. Rapp, D. McLean, J. Suhu, J. Schaefer, R. Uppa-Baker, A. Melstrom, J. Hartvigsen, J. Mayen, F. Hinterman, E. January 6, 2021. Mars Oxygen ISRU Experiment, MOXIE. Space Science Reviews. 217, 19. Bibcode 2021 SSRV. 217, 9H-DOI 10.1000/S1120-020-00782-8. HDL 1721.1/13181.6.2. ISSN 1572-9672. S2 SID 10639868. Butyl, Allard, April 15, 2015. NASA announces Mars 2020 rover payload to explore the red planet. NASA. Archived from the original on February 19, 2021. Retrieved February 25, 2021. NASA device extracts breathable oxygen from thin Martian air. The Irish Times. Archived from the original on April 22, 2021. Retrieved April 22, 2021. ABCDE Potter, Sean. April 21, 2021. NASA's Perseverance Mars rover extracts first oxygen from red planet. NASA. Archived from the original on April 22nd, 2021. Retrieved April 22nd, 2021. Carrot Kaplan, David, Baird, R. Flynn, Howard, Ratliff, James, Aranam, Cosmo, Jenkins, Philip, Landis, Jeffrey, Skimmon,
Evet,
David,
Microsoft
Johnson,
Dave'de bu
Kenneth,
ciddi ve
Carl Mann,
ağır başlı bilimsel
Paul,
tebliğ için
2000.
teşekkür ediyoruz ve
The
aslında Microsoft
2001
Dave'in
Mars in situ
bu
propellant
performansıyla
production precursor MIP flight
televizyonlarımızda
demonstration project of
bilimsel unvanıyla ve bilimsel konularda ahkam kesen pek çok kişiden daha ağırbaşlı ve vakur bir üslupla bu bilimsel makaleyi bize aktardığın hakkını teslim ediyoruz. Şimdi benim de bundan sonraki amacım Microsoft Dave'in okuduğu ve altını çizdiği kısımları Türkçe'ye çevirerek mümkün olduğunca izah etmek ve yorumlamak.